everyone, I'm Justin and today I'll be talking about Euler's method. To understand how it works geometrically, let's look at this diagram using a simple curve y is equal to x squared. The gradient or slope at any point is dy over dx, which is equal to 2x. Imagine our starting point to be xn and yn and our step size, which is the interval size or the difference between each x point. Instead of following the curve, Euler's method calculates the exact slope only at our starting point. If we sub x equal to 1, our gradient is 2, which means the Euler's method assumes the slope stays completely constant until our next entire step size. We project a straight tangent line until we hit the next x value, which is xn plus 1, which undershoots the point xn plus 1 and yn plus 1 at the curve, as a straight line cannot perfectly track a curve. This gap is called the approximation error. We can derive Euler's method formulas as seen here. For the x value, we just take the initial value plus the step size as seen from the graph. Since the slope is rise over run, which is the difference of y over the difference in x, we can derive a formula. The change in x is just our constant step size, and the slope is determined by our differential equation function f, xn, and yn. We substitute both to get the equation yn plus 1 is equal to yn plus h times fxn yn. We are given the differential equation and an initial condition of 0 and 1, and we want to find the value of y when x equal to 1. As set up our step size, h is equal to 0.5 in cell A5. Our initial x value of 0 is in cell D4, the initial y value of 1 is in cell E4, and our slope column is in cell F4, which calculates our differential equation. The formula typed here is d4 to the power of 2 plus 2 divided by E4. There are no dollar signs here because we want these references to dynamically shift as we drag the formula down. Our x value is in D5. We use the formula D4 plus A5. The dollar signs lock our step size absolute reference, so Excel always pulls down from cell A5. To calculate our next y value in cell E5, we implement Euler's equation using the formula E4 plus A5 times F4. This takes our previous y, adds our log step size, and multiplies it by our previous slope. By highlighting row 5 and dragging these formulas down, Excel instantly computes our second step. At x equal to 1, our final Euler method approximation gives us a value of 2.5625. I've created another table with a small step size of 0.1 to see how different the values are, and the value for an x equal to 1 is 2.4026. To evaluate the performance of our numerical approximation, we must compare it to the exact analytic solution found by calculus using separation of variables. As you can see here, we can actually cross multiply and then integrate both sides to find y, you times 2, and to find the constant c, you sub in x is equal to 0, as when x equal to 0, y is equal to 1, and you can find c is 1, square root both sides, square root the entire equation, and your y, you sub in x when 1, and your y becomes 2.3805. We calculate the absolute error by taking the actual value, which is 2.3805, minus the value we got using Euler's method, which is 2.5625. And when comparing to the values that we get when the step size is smaller, which is 0.1, there is less error, which shows that the smaller the step size, the more accurate Euler's method is. Notice that our Euler method overshot the true value. This occurs because the actual slope of our true curve decreases as y increases. Because Euler's method assumes the slope calculated at the beginning of the step remains completely constant across the entire 0.5 interval. It projects a straight line that flies right over the curve.